Okay, now let's get into maybe a more fun problem, and it's going to be a stepping stone to maybe help you understand why it's important to use these formulas and to actually analyze a problem. This is the scenario. I have an oil well, and I'm willing to sell it to you, and I'm willing to guarantee that you get $20,000 a year each of the next 10 years, and I'm willing to buy it back from you at the end of that period of time for $200,000. That means over the next 10-year period of time, I'm going to give you $400,000. 20,000 times 10, okay, gives you $200,000 plus the $200,000 at the end is $400,000 that you're going to get. And let's also assume in this particular case that interest rates now are at 10%. That's the money that you're going to require on your money. Now, since I'm going to give you $400,000, how much are you willing to pay me to purchase this oil well? No risk. We're ignoring that for now. You're guaranteed to get this money. Okay, let's break this out again into the timeline. And we draw our line and we see that we're going from today is our present, and we have 1, 2, all the way to year 10. And we see that in this particular case that we have a series of payments of $20,000, right? We also see that we have a single sum amount of $200,000 at the end of 10 years. The rate is 10%, and what we want to know is how much that amount is worth today, given that there's a 10% return or 10% interest rate. I mean, if you're going to buy an investment, you want to know what it's worth today. You want to know its price. Just like if you're going to go out and buy a fat cattle, you got to know the price. You know, what is it worth today? Okay, same with this investment. How do we determine that? Now, you notice that we have an annuity and we have a single sum amount. That's where we said we're going to start using mixed cash flows. This first annuity, notice that we're trying to find the present value of a uniform annuity, so we're going to use the present value of a uniform annuity formula. We also have this $200,000 single sum, and we also want a present value, so we're going to use the present value of a single sum of money formula. And you can go back in your chart and you can see where those formulas are coming from. Now, if we look at this first component is the present value of the uniform series of this $20,000 per year, and the second component is the present value of that single sum amount. If you have your calculators, I suggest that you plug this in to make sure your calculators will do this. What we have then is we have 10 years, we have 10% I. Notice that we have a $20,000 annuity. We also have a $200,000 future value. We compute it, and what is our answer? Now, how can that be? Why would you only pay me half of what I'm going to pay you? Is that the fair market value at 10% for that oil well? Now, to help understand that this actually works, I'm going to give you another scenario. Remember, the question was, do I have to borrow it? I said, no, it's in your bank. You have a choice. You can leave that $200,000 in your bank, or you can give the $200,000 to me in return for this series of money. Now, let's say that instead of giving me or buying this oil well, you leave that money in the bank. You have $200,000 in the bank, it drawn 10% interest. How much interest could you pull out of the bank that first year? $20,000. Isn't that exactly what you would have gotten if you bought the oil well? You pull that money out and you spend it, or do whatever you want with it. You still have $200,000 in the bank. How much interest do you earn the second period? $20,000, exactly the same as you'd gotten if you'd had the oil well. And let's say you repeat that to the 10th year. How much interest would you get on the 10th year? $20,000. And how much would you still have in your bank account? You'd have $200,000. So either way, you're getting 10% on your money, right? So what a 10% rate of return or 10% earnings on your money, how much should you pay for this investment? It'd be $200,000. If you paid less, you'd be better off, right? If you paid more, you'd be worse off. So what is exactly the market value, the price of that oil well today? $200,000. It's important that this sinks in, because how do you establish any value of any investment? And hopefully it becomes clear. If you base it on just on gut feeling, you obviously can come up with very wrong answers. These numbers help fine-tune to help establish what is the true value of any investment based on the market conditions of rates of return or interest rates. This is how you establish the price of an investment. Okay, this next problem is not going to be as fun. And in fact, you could solve this with just 5 keystrokes on your calculator. The purpose of this is to help illustrate clearly what we mean by beginning of period and end of period cash flows. So I recognize that this is an easy problem to solve, but I'm going to complicate it. So we dissect a problem looking at beginning of period and end of period cash flows. And it's important that you follow this. Otherwise, there's some problems that you're going to run into in the real life as well as these homework problems that are going to stump you if you don't understand the difference between this concept. And the way I've constructed this is we're going to look at this as a retirement, and we're going to say we're going to put $1,000 in a savings account drawing 10% at the beginning of each of the next 30 years. Okay, up till now we've always talked about putting things in at the end of the year. Now we're going to say what happens if it's at the beginning of the year. If we look at this in our timeline, you'll notice some interesting things. One, the first $1,000 comes in today at the beginning of the first year. Also notice that we said we're going to get 30 payments. Why does the timeline end at 29? Okay, it started at 0 and you get 30 payments, and the 29 is the beginning of the 30th period. We said the payments were at the beginning, so 29 is the beginning of the 30th. Okay, that's your first important aspect to recognize in this. Now, if you notice here on the slide where I've highlighted the numbers in blue, those we can restate this to say that there is a 29 end of period cash flows of $1,000. Notice that the first payment, the first $1,000, is not highlighted. We're going to handle it separately. We are going to handle the blue with our formula for the present value of a uniform annuity. And we can do that because we're only looking at the end of period cash flows. Now what's critical and easily missed is to recognize that in this formula, there are only 29 end-of-period cash flows, not 30, there's 29, because we're ignoring that first $1,000. We can calculate then, again, by taking the 29N, 10% I, $1,000 payment, zero out the future value, and we come up with $9,370. That's only the present value of the 29 payments, not counting the first payment. And we count the first payment by adding it to that amount. And since at time 0, there's no discounting that needs to take place, so the answer is $10,370. And if you punch that into your calculator using the annuity dues, you will get this same answer. Okay, again, this was solved as mixed cash flows. If you look at the formulas, we basically solved the present value of the 29 end-of-period cash flows, and then we added this single sum amount, did the arithmetic, and it comes out to $10,370. Again, the purpose of that was just to help clarify what we mean by end of period versus beginning of the period cash flows. This is a problem for some of you may be of interest. Many students have to borrow money to go to A&M, particularly now with the tuition and fees where they're at. So just for tuition and fees, you're paying probably close to $10,000 a year. So I'm supposing that we have a student starting that needs to borrow $10,000 a year to go to A&M. And we're going to suppose that the student can actually graduate in 4 years. And we'll also suppose that the parents are taking care of the living expenses. So you're just borrowing the $10,000 at the end of the year for the tuition and fees. We're also going to assume that we have a bank that's only going to charge 6% interest while you're in school. On graduation at the end of 4 years, the student agrees to pay the loan off over 10 years at 10% interest. That's typical of some types of loans where you have a lower rate and sometimes no interest rate while you're in school, and you don't have to pay anything on it either. It's only after you graduate that you have to worry about it. Okay? And it's very convenient because sometimes students borrow that money without ever thinking about the fact that you might have to pay it off. So we're going to look at it now. We're going to assume that the payments are going to start at the end of 5 years. 1 year after graduation, but interest starts accruing 10% at the end of 4 years immediately after graduation. What we want to calculate here today is the annual loan payments. For this student, is borrowing tuition and fees. That's all he's borrowing for 4 years. Agrees to pay it off in 10 years after that at 10%. What's that payment going to be? This problem, again, has to be solved sequentially. In this particular case, let's look at the numbers in blue. We agree that he's going to borrow $10,000 at the end of each of the next 4 years. And what we want to know is how much will we owe the bank upon graduation? Which formula do we use to solve this V4? Okay, it's a future value of a uniform series. Our annual amount is $10,000. We're going to pay 6% to the bank. There's 4 payments. We plug that into our calculator, 4N, 6% I, zero out the present value, 10,000 payment. And what we see is that we would owe the bank at the end of graduation $43,746. $40,000 of that was principal that we borrowed, so the interest that we would have accrued over that 4-year period of time is $3,746.16. What that means is that upon graduation, we owe the bank that much money. And we can think of it then as taking out another loan over a 10-year period of time, starting at graduation at time 0, and we're going to pay that off over 10 years at 10% interest. And the question we're asking is, what is the loan amount, that equal annual uniform payment of principal and interest that we pay the bank at the end of each of the next 10 years? How do we solve for that A? Is this a present value or future value? Is this a uniform series? So we are going to use a present value of a uniform annuity formula. In this particular case, the present value is the money that we owe, $43,746, 10% interest over 10 years. We plug that into our calculator. What we determine is that we would have to pay the bank back $7,119. Now, let's put this in perspective. You do well in your courses, and you go out and you get a job paying $30,000 a year. After you pay the bank off, what's your net salary for that first 10 years? It's 30 minus the 7,000. We'll round it to 7. So basically, your $30,000 job now has been reduced to your net of $23,000. If that's not grim enough, let me also suggest that maybe when you graduate, you finally decide you want to get married, and your spouse has a $7,000 annual payment for her A&M degree. And let's also assume one of the spouses decide to stay home instead of work. Now what does your $30,000 job go down to? Is that a little sombering? Okay, looking at capitalization. Again, we're going to expand or use these formulas to look at some other issues. And I've mentioned before that some of you in your farm management classes or your production classes should have, and I assume that you had, talked about the cap rate in context of farmland prices. But many of your classes may not have told you or have given you an intuitive feel of what that means or where it comes from. Today we're going to figure that out. The US PV, the Uniform Series Present Value Factor, assumes a finite number of periods, N. We just did it on the student loan, and there was 10 periods. It was finite. It was countable. We knew how many it was going to be. Some investments like land or others like a permanent endowment, like the A&M Permanent Endowment Fund, endowed oil wells, have an infinite stream of income of dollars per year. It goes on to perpetuity as long as we can think, or as long as we can imagine. Okay, if we look at the present value of an infinite annuity, we can find the present value of a finite annuity. Now we're saying, what is the present value, or what's the value of an income stream that goes on forever? Now to do that, I've basically taken the US PV factor and placed in it the numerical representation of that. And you can see that presented 20 pages back in the notes. But what we're going to do now is we're going to ask, what happens if n approaches infinity? Okay, this is mathematics that you may or may not have had before, but it's just basically saying what happens to this equation if n gets infinitely large. And that's what we're asking, right? N, instead of being 10 years or 100 years or 200 years, we're saying, what if it's millions and millions and billions? It just keeps going on. I've placed this again on the slide. Let's first look at this. What happens if this N gets real large? Remember that 1 plus R to the minus N is equal to 1 over 1 plus R, okay, to the nth by the rules of exponents. What happens now to this quantity as N approaches infinity? As N gets bigger, that denominator gets increasingly large, right? As a denominator gets increasingly large, then what happens to the whole quantity? It gets smaller and smaller till it approaches 0. So this whole quantity approaches 0, and it gives you then 1 minus 0 over R, which is equal to 1 over R. No mystical magic or hand waving here. It's just as N gets big, this whole quantity collapses to 1 over R. And sure enough then, the present value of a uniform annuity to perpetuity becomes that annuity multiplied by its capitalization factor. Now, if we had a rate of 3%, the cap rate, 1 divided by 0.03, is 33%. So, okay, if you had an annuity that paid $100, you would multiply that annuity by the 33 to come up with its present value, or what it's worth. If the rates go to 5%, then because the amount is constant and you demand more money on your investments, then you would pay less for it. So the cap rate goes down. As interest rates go to 7%, okay, the value of that annuity is now only worth 17 times the annuity. Whereas if it's 3%, it's worth 33 times that. Okay, still a little hazy, so let's bring it to something a little more closer to home. Let's suppose a parcel of land promises to return $100 per acre, whether it be cotton, wheat, or whether you just have hunting rights on it, where you assume that you can get $100 per year per acre. What is the capitalized value of that land if interest rates are 3%, 5%, or 7%? First of all, okay, we're holding constant the returns, and we're assuming that returns is something that land's going to be there forever, and we're assuming that we're going to get $100 forever for that land. If we can make 3% on our money, or that's what we insist on, getting 3% return, then we would multiply that 100 by the 33.3%, and it would be $3,333 per acre. Now, if interest rates jump to 5%, then you would multiply that by 1 divided 0.05, or the cap rate of 20, so it'd be $2,000 per acre. And if it's 7%, then your value would be $1,428. Or you can think of it another way. Let's say that you have an acre of land out there, hundreds of acres of land, and you've got the money and you want to buy it. And you think that you can get $100 per acre of that, farming that or hunting or whatever use that you have on that land, and it's selling for $3,333 an acre. What is the rate of return that you're going to get on that land, holding everything else constant? 3%. You satisfied with that? Well, if that's all you can get on your money, or if interest rates are 3% and you can borrow at 3%, maybe okay. On the other hand, if you can get $100 per acre and it's selling for $1,400 an acre, now what's your rate of return? 7%. Now you're a little happier, right? Okay. Well, let's say that the land is selling for $2,000 an acre. You get $100 per acre for that land. If you anticipate that interest rates are going to drop, do you buy the land? What happens if you buy it at $2,000 an acre, interest dropped to 3%? What happens to land value? You buy for $2,000, you sell it for $3,000. You know, buy low, sell high. You know, but if you think interest rates are going up, then what do? You either sell it or you don't buy it, right? There's a lot of information packed in this little capitalization factor that you can use to help evaluate what property values are, whether it's real estate for an office complex or land or anything that's got returns a life to it. This can help give you some rough numbers in your mind as to what its value should be.